Usually applies when variable power in numerator or denominator, when there is a variable power in the numerator or denominator. Uh, the idea being that it's not nth rootable. All right. So we'll get into that in a few minutes. But the condition is we're going to have a series of non-zero terms, right? Just like everything else. We don't want it to be a series of zero terms. Oh, well, maybe we do. If it were a series of zero, then it would be pretty easy to figure out whether it converged or diverged. So on a test, maybe, but yeah, it doesn't really advance the plot. All right. So what we want to do is determine convergence based on this ratio. All right. A sub n plus 1 is one additional term down the sequence. But you get it really just by substituting an n plus 1 in for your n. Okay? I don't know why I thought this teensy tiny bit of room would make sense for this. This is what it is. All right. So we have a variable power in the numerator and not in the denominator. And what I mean by not nth rootable is because when we get to the root test, we're actually going to take the nth root of something that is raised to the nth power. That only happens if the power is on the top and on the bottom. Here, we're looking at the power of n being on the top or on the bottom, not on both. All right, because if it were on both, then we would be looking at the root test. Okay, so that's really all I was talking about there. It just sometimes gets lost in the translation. All right, so on the top, oh, actually, I don't need the sum. We're doing a limit. All right. I was thinking of something else, and I started this way. So limit as n approaches infinity of the absolute value of a sub n plus 1. So all of this stuff replacing n's with n plus 1. So 2 to the n plus 1 over n plus 1 factorial. And then we're going to take that and divide it by the original a sub n. All right? So 2 to the nth over n factorial. All right. So, you think about the conditions again. Usually applies when there's a variable power in the numerator or denominator. So, you think about a case where it's like, let's say it's 1 over 3 to the n. Yeah, technically you could use something like a ratio test for that. I mean, it seems to apply the same idea. But then you might be thinking, well, why would I do that when I can use, let's say, for example, the p-series test, or a comparison test of some kind. So you don't necessarily want to go to the hardest thing. You want to go generally to the simplest thing. All right, so we want to simplify this. The idea being that we're going to get an answer that's either less than 1 or more than 1. If it's exactly equal to 1, then it is the dreaded inconclusive situation. And it means that the root test has failed us. I'm sorry, the ratio test has failed us. All right? It didn't tell us anything useful. But you got to get past the algebra. All right. The bottom part is not the challenging part, it's the top part. Now, 2 to the n plus 1, that's the result of base at the exponents. So let's undo that. Make it 2 to the nth times 2 to the first. Now, the weird part is the factorial component, because it doesn't really seem like there's much you can do. But there's actually something very useful that can come out of this. And that is, if you start just listing out what n plus 1 factorial might be, well, you start off with the number itself that's factorialized, and then you multiply by consecutively lower values, right? So the next one in the multiplication would be n plus 1 minus 1, so just n. Then n minus 1, then n minus 2, and so on. That part in and of itself is n factorial. So what we get from this is the idea that n plus 1 factorial is the same as n plus 1 times n factorial. Right? Just by listing out a few terms of the product, you're able to come up with that. Right? So if it were n plus 2, for example, factorial, it would be n plus 2 times n plus 1 times n factorial. All right, so you have to go a couple of steps in order to get to the n factorial part, but once you do, beautiful things are going to happen, because all the stuff, I think, in this problem that was making it difficult cancels away. 2 to the nth is gone, n factorial is gone. So this would be the same as the limit as n approaches infinity of 2 over n plus 1, which would be 0. Fun fact, 0 is less than 1. So we now know, therefore, the series in its original form, 2 to the nth over n factorial, converges by the ratio test specifically because we're dealing with a case that's less than 1, but I think that's writing too much. You've shown what the limit is, and that's the ratio test. No fun abbreviation for this one. RT could be root test, so unfortunately we have to write one out. Finding the RA test, yeah. The rat, yeah. The rat and the rot, that works. All right, so a little bit more funk involved in this. It means if it gives you a 1, then it means it's it.
So I'm saying as long as it's not on, is that get
Yes. All right. So the next two examples are very similar in structure, but so I'll put a star on B. But I've experienced in the past that whether people say it or not, the whole factorial thing tends to throw people for a loop. So I'll do C right now, just to kind of make sure I hit that concept the second time. All right. So. Limit as n approaches infinity. I have a big old absolute value here. On the top, it's the n plus 1 term. So if I'm replacing each of these with an n plus 1, we're going to be looking at n plus 2 factorial over 3 to the n plus 1. And then on the bottom, the original factorial in its original form. And also, a to that, basically. So you have to clean this up. The exponential part of it's easy enough to handle. So that's the keep the base out of the exponent stuff. But the n plus 2 factorial. All right, so n plus 2 factorial. If I were expanding that out, I would start with an n plus 2. Then I would decrease by 1, so it become n plus 1. Decrease by 1 again, so n. Decrease by 1 again, and so on. All of this stuff is the same as n plus 1 factorial. All right, so I want to rewrite instead of n plus 2 factorial, I'm going to write it as n plus 2 times n plus 1 factorial over 3 to the nth times 3 to the first. I stopped with the n plus 2. I didn't write it as n plus 2 times n plus 1 times n factorial. The reason I didn't do that is because I don't have an n factorial to cancel. I have an n plus 1 factorial to cancel. So it made sense to stop it there. Cancellations galore. All the hard parts are gone. We're looking at the limit as n approaches infinity of n plus 2 over 3, which is going to be equal to infinity. Again, we're just looking at 1 as our benchmark. Less than 1, converges, more than 1, diverges. Right? This is way more than 1. Right? So this original series is going to diverge, again, by the ratio test. Right? So diverges by the RAT. I had more room to roam, but all right. In the case of the root test, similar structure. You'll notice that it has exponentials in it. Sometimes they have factorials, not always. Right? The idea is that you have the variable power top and bottom. So it becomes nth rootable. Right? So it will converge. Our series will converge if the nth root of our series has a limit that's less than 1. Right? It'll diverge if it has an nth root limit that is greater than 1. The infinite root? Well, you're approaching something. How is it? Oh, conceptually, like, why is this true?
How does that work? Yeah, I feel like
Or how does an nth root work?
that's why I feel like take the word back and it doesn't practically stand up until you that's one.
So the idea generally is that where this goes, this is going to follow, because it's basically the same function, just sort of in disguise. So whether it's a radical function or otherwise, as you go out to infinity, if it's a large number, or a function that's, try to think how to phrase it in a nice way. So a function that's made up of large values, it would be approaching, if it's going to converge, it's going to be approaching a particular sum. All right? Its root would also, on a much smaller scale, be approaching its own sum. There is a relationship between those two sums. Right? It doesn't matter what the relationship is, it just means that as one goes, the other follows. But it would only happen if the limit is less than 1, because what's going on here is it's converging on a fractional value. Okay? So something very small for the root function that almost, I don't want to say it guarantees, well in this case it shows that it guarantees, but it's demonstrating that your variation is going to be limited, right, minuscule, right, so bless you. Yeah, so as that small function is converging on its small window, the larger function correspondingly would be converging. Even though it has a larger window, it would still be converging necessarily because they're hand in hand. Right. So, how do we do it? Well, we find the limit of the nth root of the absolute value of the a sub n term. Right? So, my recommendation would be to pull out the a sub n and manipulate it. Rewrite it as a power of n if you can. All right. In this case, it would be e squared over n to the n. All right. What we're looking for is the limit as n approaches infinity of the nth root of that. Which is to say, the limit as n approaches infinity of just e squared over n. All right? So this here, that is the limit as n approaches infinity of the nth root of a sub n as an absolute. Now, how you handle the absolute is up to you. Really, as long as you're aware of it, everything is going to be all right. You don't actually have to include absolute value symbols. Since n is starting at 1 and going out to infinity, the denominator n is always going to be non-negative, and the power is constant. The numerator is constant. So we never have any concern that there's going to be a negative quantity in here, right? But if we did, we would drop anything, right? So I want to make a determination of whether this converges. That's only going to happen if this limit is less than 1. All right, so constant over infinity is equal to 0, and 0 certainly is less than 1. So this converges by the root test. All right, converges by the root test. Now, it's very important that you're aware of the conditions behind these tests. So it's not like, oh, I'll just use the ratio test here. But you don't use the ratio test if it applies. I can only use the root test if it applies. How do I know it applies? It's in this step, going from blue to black, that I know that it applies. Hopefully I know before that. But here it's confirmed. The idea is that taking the nth root should make the power of n go away. Right? If it doesn't, then you have no business using the root test. Right? It has to be whatever fraction you have has to be nth root above, which means each part has to be raised to the nth power. That cancellation needs to happen, otherwise the nth root test is not appropriate. Now, in part B, I mean, that's tailor-made. Not that Taylor. Taylor as in clothing. So I'm looking for the limit as n approaches infinity of the nth root of my a sub n as an absolute, but we'll worry about the absolute separately. All right. Because these two match up and cancel each other, we know that we're on the right track using the root test. The result of this limit is just 3 over 2. Which is not less than 0, less than 1. So it diverges by the root test. Or the rot, if you're so inclined.